Okay, this is Paul Geyer, and I'll be the presenter for this webinar today. Energy efficiency upgrades for air distribution systems in buildings. I want to place a little bit of emphasis on some of the wording there. Air distribution systems. That means from the fan, as an example, in a typical building HVAC system, from the fan through the ductwork, through into the occupied space, and then the return of the air back to typically the fan room. So there's nothing that we'll be talking about today about things like chillers and boilers and so on and so forth, which is where you get the typically the chilled water or the hot water, which is pumped from a mechanical room to the air handlers, typically in a multi-story building. That's kind of the picture we want to have in our mind as we're talking about this. Is a multi-story building. On each floor, you have a fan room and a fan in it. And off somewhere else in the building is a mechanical room where you've got typically a boiler heating hot water or possibly steam for heating, and then a chiller to produce the cold water. And these are the heating and cooling media that you pump to the fan rooms on each floor of the building. And on each floor of the building, typically you've got an air handler is a box with a fan in it, and it'll have a heating coil for hot water typically, or chilled water for cooling. And then the fan pushes air through the coil, the heating coil or the chill or the cooling coil, into the duct system, and then through the duct system, through some filters probably, and then into the occupied space. And then the air is returned to the fan room, and it recycles, or a percentage of it recycles. So that's what we're talking about, is the HVAC system from the fan through the occupied space. And this is a discussion of upgrades, and implied in that, obviously, is that what we're talking about is existing buildings, old, probably of different ages, but they're older, and they may have older types of HVAC systems. And some of these older types of air distribution systems are energy inefficient, and we're talking about upgrading them. So, and a bookkeeper, a housekeeping item to mention is that the way we move forward with the webinars is I press on with the presentation for 50 minutes, and then we take a 10-minute break, come back, do another 50 minutes, 10 minutes, 50 minutes, 10 minutes. This just being a 2 PDH or 2-hour webinar, we'll just go through that cycle twice. This is, of course, an interactive webinar, and questions and comments are encouraged and welcome. And we have two ways of communicating. One is that you can just speak right up on the audio stream, and I will respond. The other mechanism, of course, is the little chat box where you can type in a question or a comment, and I'll try to keep an eye on that as we move along and respond. Okay, here we go. This is kind of what I'll be touching on today is first some comments, just an overview of the basic fundamental types of air distribution systems, and the air handling systems, and we'll talk about the air distribution fans. Again, I'll typically be talking about a multi-story building, and the one where you've got a fan room on each floor, and then, like I say, off somewhere else in the building is a mechanical room that has the boiler and chiller in it. And so we'll be talking about the fans and filters in the air distribution system. Filters, of course, are there for air quality purposes, but they are an impediment, you might say, in the air distribution system. The air has to be forced through the fans or through the filters, and so that uses up energy. So filters, what can we do with the filters to improve energy efficiency? Then we'll talk about variable speed drives. One of the industry developments in the last decade or so is the development of variable speed drives, so that when you don't need to have a lot of cooling or heating in a building, you can reduce, with the control system, you can reduce the speed that the fan is turning at, and that saves energy. We'll talk about this and other modifications to the control systems. We'll talk about premium efficiency motors. These are high efficiency motors that electric motors that have been developed. Let's see, I've got chat. Do we have to respond to inquiries to get credit on this class? Hisham, you'll need to respond to that. Hisham is the guy at headquarters. Okay, and then we'll talk about the improvements that have been made in the belt drives in the fan room. There's an electric motor turning the fan, and it's connected to the fan by a belt. And there have been things that have been done in the design and marketing of these belts that have made them more efficient, and we'll talk about that. And then lastly, consider the role of a testing and balancing contractor for your building, because frequently the system for the air distribution system, for various reasons, gets kind of blocked up. Let me see, I got another chat here. What inquiries? Okay. Hisham, you'll need to respond to this inquiry or this chat comment. What inquiries? So the role of the testing and balancing contractor, because over time the air distribution systems get out of whack and you're not delivering the right quantities of cooled and heated air to the spaces that the design calls for. Okay, and Bennett asks, for example, will you ask us to verify our attendance periodically? Hisham, you're going to need to answer that question. I don't think you need to verify your attendance periodically. I think that if you're logged in, there is an assumption that you're sitting up straight in your chair and paying attention. Okay, and so these are the things we'll kind of touch on today. Okay, there we go. By way of introduction, here's a little bit about me and what I've been doing to make a living for the last few decades. For 35 years, I was what I characterize as a straight-ahead designer, cranking out drawings and specs for the construction of buildings and fairly broad spectrum of infrastructure features. I got registered in a few different things along the way, but I'm basically a mechanical engineer. That's my degree and my first registration. And I have had quite a bit of design experience with HVAC systems. And a lot of that was had to do with retrofitting HVAC systems in existing buildings usually for energy efficiency reasons. After that, 35 years, I had an opportunity to do something that I had always had an interest in. And so for an additional 9 years, I was in what might be called the public policy arena, where I was a principal staff advisor to the California legislature on capital outlay and infrastructure issues. And there would periodically be issues that would come up dealing with energy efficiency and sustainability and green buildings and so on and so forth. And I was supposed to be able to answer all the questions for the legislators. Okay, now just an overview of air distribution systems. There are the air distribution system is essentially, it's the ductwork. It's the fan plus the filters plus the ductwork and the controls that control the temperature in the occupied spaces, heat it up, cool it down. And there have been a lot of improvements that have been made in energy efficiency for different features of a building. And so one of the reasons that you may, if you've got older buildings, if you will, that you may want to invest some time and energy and money into upgrading them, is that there may have been improvements made in other features of the building that have reduced the heating and cooling load or cooling load in the building on the HVAC system. And as a result of these energy efficiency improvements in other features of the building, you can cost effectively invest in energy improvement features for the HVAC ductwork and fan and the distribution system. An example, a very good example, is lighting in building. Lights, of course, are a substantial part of the load in the buildings. And there have been great improvements that the manufacturers have made in the lamps that are now on the market. They're much more energy efficient than they were back in the days when you largely had incandescent lighting or maybe some fluorescent. And so this is going to reduce the load on the building. It'll reduce the amount of cooling that you need to do to compensate for the heating that's being done by the lamps in the lights. And there are lots of other different things. On the other side of the coin is computers. They, since they have become part of the office environment, they do impose a cooling load on the HVAC system. Quite a bit of load comes from computers. So this is the other side of the coin, where you need more cooling in spaces. Okay. Now, how big a energy consumer is the air moving system? Is basically the fan and the ductwork and the discharge mechanisms, whatever they might be. Well, the EPA has of course been active in this area for a number of years, and they've kind of concluded that the ventilation system or the air distribution system is consuming about 7% of the energy that is consumed in a building. And this kind of pie chart kind of illustrates that. So the cooling equipment, the chiller, is the biggest consumer of power. That's around 29%. Office equipment, that's the computers and printers and all of that sort of stuff. Lighting, about 22%, and so on and so forth. And space heating is also a consumer of power, not as big a consumer as cooling, though, in typical buildings. But the ventilation is consumes about 7% of the electricity in typical buildings, office buildings. Now, air handling systems. There are basically two types of air handling systems, constant volume and variable air volume. Now, with a constant volume system, the quantity of air that's coming out of the fan and going into the ductwork distribution system remains constant. And the fan pushes that quantity of air through the ducts to the occupied space, where it discharges into the space and provides cooling and heating. And the temperature in the space, in the occupied space, of course, is controlled by a thermostat. And so one of the realities with a constant volume system, and these are the older systems, but these are the ones that are going to be in these old buildings that you're retrofitting. And the drawback, if you will, of constant volume systems is that there's only one thermostat, and that thermostat would, if it's getting too cold in the space where the thermostat is, the thermostat tells a control valve on the chilled water line back in the fan room to close down a bit and cut down the quantity of chilled water that's going through the cooling coil, and thereby allow the occupied space to warm up a little bit. But the fundamental drawback with constant volume systems is that there's only one thermostat. The only person that's happy on a floor, you might say, is the guy who's got the thermostat in his office, and he can set the temperature at whatever he likes, and that's fine for him. But everybody else on the floor doesn't have control over the temperature. So that's the big drawback of the constant volume systems, which are the old systems. The newer systems, and they have been the industry standard, you might say, for 2 or 3 decades. These are variable air volume systems. And with variable air volume systems, you have the air being pushed into the ducts, and there are a lot of ducts often to serve different spaces. But you have a control device or a mixing box or a box, a control box, just before the air discharges into the occupied space. And so, and there's a thermostat in that space that controls that VAV, variable air volume box. And so if it's getting too cold in the space, the thermostat tells this VAV box to close down and shut down, reduce the volume of air being discharged into the space. And then vice versa, if it's getting too hot, the thermostat tells the VAV box to open up and put more air into this space. And so each discharge point for the air into the different occupied spaces has a control box, and it has a thermostat. So they're all a bunch of thermostats all over the place, and they're opening and closing these VAV boxes, variable air volume boxes. And this provides substantial improvement in occupant happiness, because they can have the thermostat set however they want it in their space. The problem with the VAV systems, though, is that if you don't have a variable speed motor driving the fan, you've still got a constant volume of air that the fan is putting into the distribution system, and the different zones are fighting each other to a degree. I want more cool air over here, and over in this other zone, they want more cool air, so they're fighting over the air. So, but in any event, the state of the art, if you will, in HVAC systems for buildings, typically these days, new buildings, is VAV systems. But we're talking here about what you can do with these older buildings that have a constant volume system, and what you can do. Now, the constant volume systems, to provide some control over the temperature, the comfort in the occupied spaces. There are kind of 4 approaches that have been used in the past. One is reheat systems. And with a reheat system, the air is cooled down back in the cooling coil in the air handler, below the temperature that is comfortable for occupants. And then when that cold air reaches a zone there at the discharge, just before the air discharges into the space, is some kind of a heating element, usually an electric resistance heater, or it could be one heater with a little steam coil or hot water coil in it. But in any event, with constant volume systems, with a reheat system, you're cooling the air down below the comfort point, and then you're heating it back up to the comfort point. And this is energy inefficient because you're using energy to cool it down, and then you're using energy to heat it back up. So, but that is an approach that is used in older buildings, in some of them. A constant volume system with terminal reheat. Another approach that has been employed with constant volume systems are constant volume variable temperature systems. And these somewhere in the building is a thermostat, or possibly it might even be outside of the building. In any event, there's some kind of a control sensor that senses that we don't need as much cooling in the building or on this floor, and therefore we will reduce, or we will allow the cold water, the chilled water, to be a little warmer before it enters the chilled water coil in the air handler. And so it resets the temperature of the cooling water or the heating water. And that is an approach in older buildings, older systems, is constant volume, variable temperature systems, where you are varying the temperature of the chilled water and the hot water. Another approach that has been used with the constant volume systems in these older buildings is a dual duct system. And this is where in the air handler you have a hot water coil and you have a chilled water coil, and you split your air up quantities into a hot air duct and a cold air duct. And so you're running two ducts to the occupied space in a dual duct system. One has hot air in it, the other has cold air or cool air in it. And just before the air discharges into a zone, into the occupied space, the a temperature, a sensor, a thermostat in that space controls a mixing box. And this mixing box is right before the air discharges into the space, and it mixes the hot air or warm air and the cold air to get it at just the right temperature that that zone needs at that point in time. And the so this allows a good control scheme for throughout a floor or throughout a building, because everybody can have their own thermostat and they can set it however they want it, and they can control the air in their space, and that's all fine and dandy. But again, this is an energy inefficient system, because you have to use energy to heat the air in the hot air duct, and you need to use energy to cool the air in the cool air duct. And then you mix these together just before they discharge into the zones. This is an older, again, this is a system that has been employed in the past in a lot of these older buildings and with these older constant volume systems. Gives a good quality of heating and cooling and control, but it's quite energy inefficient. And then the fourth fundamental type of constant volume system is a multi-zone system. And this is, if you can kind of visualize back at the fan room in a straight constant volume system, the air is just pushed into one big duct as it leaves the fan room. But you can divide that big duct up into a bunch of a certain number of small ducts, maximum typically of about 10. And so, and then you can put a control device, and it can be dampers on each of these 10 small ducts, or it can be little heating or cooling coils. And so if you, with a multi-zone system, you might have 10 zones or ducts. And so that means that on the floor, you can have 10 thermostats. And so you get a degree of control. Again, this is an energy inefficient thing to be doing, but it is what was done on these older systems in older buildings. So these are typically the kinds of HVAC systems that you're going to be faced with in these older buildings where you're trying to implement energy efficiency improvements. The reheat systems, the constant volume variable temperature systems, the dual duct system, and then the multi-zone system. And then the variable air volume system is the system that's kind of the state of the art today and with new buildings. And that's not what we're really about today. So let's see now, we already zipped through these different types here. The multi-zone, and then the VAV systems. And this is just a picture of a typical VAV control box. So this is located right at the end of a duct run just before it the air discharges into the space, and it is controlled by a thermostat in that space. And when more, as an example, more cooling is called for by the thermostat, this box opens up and admits more air to that space. Now let's see where we, okay, now let's look at the features of the air distribution system that we have to work with to accomplish these energy improvements. First of all, there is the fan in the illustration I keep talking about, a multi-story building where you have a fan room on each floor and a big fan in that fan room. And So there are things that we may be able to do with that fan. Then there are the air filters on the system. These are for air quality, and they are typically, they may be located at the discharge point of the air in the ducts from the fan. The filters might be located there, or sometimes they might be located just before the air discharges into an occupied space. And then we have the ducts themselves. And then there's, of course, the control system. So the air distribution fans, filters, and the ducts. These are the things we've got to play with, or to work with. So what are the best opportunities that may exist for energy improvements with these older systems? Typically constant volume, and they may be dual duct, they may be terminal reheat, or they may just be straight constant volume systems. The best opportunities then fall into 4 categories, or 3 categories actually. Optimizing the zone level performance, and we'll talk about that in more detail. Converting a constant volume system to a variable air volume system. This is a good energy improvement step. It is kind of tricky, if you will, to design the conversion, and it needs to be done by a mechanical engineer who has substantial experience in converting constant volume systems to VAV. But converting a constant volume system to a variable air volume system is a really good thing to try to do from an energy conservation standpoint. And then the other third major improvement that might be made is to right size the fan. In other words, this is typically directed at the situation where you've got an older building. The lighting load has been reduced because of the improvements that have been made in the lamps that are available on the market now. Perhaps the windows, the glazing may have been replaced, upgraded to reduce the solar load on the building, shaded or reflective glazing. And these things can result in an older building where the fan is too big for its operating environment today. And so if you can reduce the size of the fan, that reduces the power consumed at the fan. So right sizing the fans is an important opportunity. So the optimizing the zone level performance. Now, what we mean there, one thing that we may mean is to recalibrate the thermostats. And the issue there is that the thermostats have a tendency to kind of, to get to where they're not functioning as well as they should be. They may be sticking or something like that. Particularly if you have pneumatic controls, and you do have pneumatic controls in some of these older buildings. With them, the thermostats with pneumatic control systems, they periodically require recalibration. And that should typically be done every 6 to 12 months in order to regulate the space temperature more accurately. Though the thermostat calibration should be checked if a complaint arises, a comfort complaint by occupants, but it's also preferable if you just write this into your routine operations and maintenance procedures for the building, and check the calibration and recalibrate the thermostats in the spaces. So that it falls into the category of optimizing the zone level performance. And another thing that needs to be done as a routine O&M activity is within the category of optimizing the zone level performance is to inspect dampers, because they periodically they get bent or they get stuck, and they're not doing what they should be doing according to the design of the system. An air distribution system, the air comes out of the fan in a big duct, and then it splits into smaller ducts, that branches that run off to different spaces. And to the design of the HVAC system calls for specific quantities of air to be discharged into specific spaces based on the occupancy and the activity going on in that space. And with all of this ductwork being split up and branches running off and this sort of thing, you need to have a method of controlling that airflow, and that's done with dampers in the duct system. And when the system is first designed and installed, it's routine to have a testing and balancing subcontractor come in and adjust these dampers in the ductwork system to provide the quantities of air in the spaces that are called for by the design of the system. And it's these dampers that frequently can get bent, stuck, and so on and so forth. So inspecting the dampers is something that should be done as a matter of routine. And hopefully when the building was designed, there were inspection plates put in place where these dampers were located, so that as the building is operating, the maintenance people can have direct access to all of these dampers and can get in there and check and see that they're operating correctly. So inspect dampers. Also If the like if you're using a dual duct system where you've got a mixing box just before the air discharges to the occupied space, that mixing box has dampers in it that need to be inspected to assure that they are functioning properly. A an important point also where there can be substantial energy savings is to prevent overcooling. Now this typically is going to would occur as an example with a terminal reheat system. You're cooling the air down below the comfort point, and then you're heating it back up, and that's inefficient. And so if you have a terminal reheat system or a dual duct system, those are candidates, good candidates for energy efficiency improvements. They can be costly, but worth it in the long run. If you do have a terminal reheat system in an older building, perhaps you can get away with disabling the reheat system completely in the summer months, and just providing cooling during the summer months. This has to be looked at by the mechanical engineer in evaluating what can be done. Now, I'm looking at my clock here, and it's just about time to take our 10-minute break. Another opportunity is to regulate the static pressure in the system. In other words, are you forcing air with the fan into the ductwork system at a higher static pressure than is necessary to move the air to the occupied spaces, or are you pushing the air into the ductwork at too high a pressure, and then you're having to throttle it down with dampers as it moves through the distribution system and gets discharged into the spaces. So if your static pressure that the fan is producing is too high, you may be able to lower that static pressure and thereby conserve some energy. Okay, now let's take a little break here. I've got 10 minutes before the hour, so let's take a 10-minute break and come back on the hour, and we'll pick up here and we'll talk about converting a constant volume system to a VAV system. And this again, this is a big opportunity with older buildings, and it's expensive. It needs to be done in a well thought out way by an experienced mechanical engineer, but it can be a very good investment of time and money. So I'll see you all in 10 minutes on the hour, and we'll pick up here and talk about converting the constant volume systems to VAV systems. So I'll see you in 10 minutes on the hour. Okay, this is Paul Geyer, and I'm back. The the big opportunity to improve energy efficiency in an older building with an older, typically constant volume HVAC distribution system. The big opportunity for improvement is to convert the system to a VAV system. But this needs to be done. Again, it's a significant redesign issue for the mechanical engineer, and it needs to be a mechanical engineer that's got good experience in this area with them. So the typical airflow requirements for VAV systems are only about 60% of that of constant volume systems. So you're moving less air, and therefore you're using less energy around, so about a 40% savings, more or less, in energy is potentially is available. VAV systems cool only the air volume that's required to meet the demand, rather than meeting demand by simultaneously heating and cooling large volumes of air. To determine whether the existing system is VAV or constant volume, you review the original design drawings, and there will typically be a schedule of VAV terminals in the equipment list that includes the minimum and maximum airflow CFM for each zone, and that is a VAV system. The conversion of an older constant volume reheat multi-zone or dual duct system to a variable air volume system is a task to be undertaken only with serious consideration and expert analysis. And fundamentally, what you're doing in converting a constant volume system to a VAV system is at each discharge point for air into occupied spaces, you are essentially just adding a VAV control box there, and a thermostat in that zone. And that essentially converts a constant volume system to a variable air volume system. Now, the difficulty that may very well arise is that if you do that, then the zones, what are now the new VAV zones, are now fighting each other for air, and this is a place where a lot of energy gets unnecessarily used. The early VAV systems did not have the benefit of variable speed drive electric motors. And therefore, this was a problem or an issue with VAV systems when they initially came onto the market, if you will. But what has made them very energy efficient now is the digital control systems that have been developed and are marketed, together with the variable speed drive electric motors. And so now with digital controls, the quantity of air that is desired, if you will, in each zone throughout the floor or throughout the building is monitored and controlled, if you will, by the digital control system. And so it adds up all of the quantities of air that are required. And then it adjusts the speed of the fan to provide just that quantity of air when it is needed. When the need changes, when more cooling is needed throughout the building, all of the VAV boxes, each of which is controlled by a thermostat, will tell their VAV box to open up and admit more air to my space. It's getting too hot in here. And the digital control systems will add up that new quantity of air, total quantity of air that's required by the fan, and will speed the fan up and provide the quantity of air that is demanded, if you will, by all of the zones. So this is a good good opportunity to save some substantial energy. Now now you have building level, what might be called building level factors to be considered in a retrofit energy efficiency project. The one of the building level factors that you need to take into account and think about is access that the contractor will have to all of the necessary pieces of the system. Checking the dampers as an example. Are the dampers on the HVAC system are they accessible? Are there access hatches so that the contractor can get at them? And if not, that is an issue, and may have a significant impact on your budget. If you're like, as an example, you're going to have to take down the entire suspended acoustic tile ceiling in order to get access to everything that you need to get access to, dampers, control boxes, etc. Then that's going to be a significant expense, and you're going to need to take that into account. If in the older buildings also, something that you need to take into account, be aware of, is there an asbestos issue in the building itself? And the rules of the game basically with asbestos are that if you can you can leave the asbestos in place if it's not going to be in occupied spaces. But it needs to be, if you're going to have to remove asbestos to get access to features of the air distribution system, then that's going to be a big impact on your project, because there are worker safety procedures and equipment and safety clothing that are going to be necessary, and those are all cost items. So that will run up the cost of your retrofit project. So you need to take these into account in determining whether to move forward with an energy improvement project on your older building, or if it's going to be impracticable or uneconomical to do so. So the then system level factors, you need to check the age and condition of the existing zone dampers and actuators. If they are in good condition, this will make the conversion easier than if the contractor is going to have to repair all of these components. This is a system level factor you need to take into consideration when you are making the decision whether to move forward with an energy improvement project. If you have an existing dual duct or multi-zone system, you need to determine whether the existing hot and cold dampers are controlled by one or two actuators. Converting these systems to VAV usually requires two actuators, so that the hot and cold air supply can be regulated independently. Having two actuators already installed usually leads to a simpler, less expensive conversion. And it's possible to add a second actuator if there is only one, but it will add cost and complexity to the project. So something to consider. If the existing equipment is in poor condition, then you would kind of consider that to be just good building management to replace the aged equipment. With new. Now, the other next opportunity to that is frequently a good cost-effective one is to right size the fan. The fan in the older building may well be too big for the load that it is currently serving. And this can be due to things like I pointed to earlier. The owners of the building may have gone through and already undertaken to do things like change out the lamps in the lighting system to reduce the load on the HVAC system, and that's frequently results in a substantial reduction in the load on the HVAC system because of the improvements that have been made in the lamps that are available on the market these days. Also, the building management may have replaced the original glazing in the windows with reflective or colored glass to reduce the solar load on the building, on the HVAC system, and even things like installing louvers or shutters on the windows may have been done. All of this resulting in a reduction of the required cooling load on the building. And therefore, that means your older fan is too big and is therefore consuming too much energy. The first step in addressing the right sizing of the fan is probably something that can be done by the building maintenance staff. Once an opportunity has been identified, it's usually necessary to have an engineer brought in to verify it and conduct a more detailed analysis to make recommendations for optimizing the system. So the maintenance personnel are an important part, but not the entire equation. So diagnosing oversized fans, the potential may exist, and building maintenance staff are the first responders, so to speak. And the first method of diagnosing the oversized fans is to measure the static pressure of the main supply fan. And it's best to get this baseline measurement on a hot, a humid day if you have a climate where you have humidity as an issue. Make sure that all fan vanes and dampers and all VAV boxes are fully open, and compare the static pressure reading with the static pressure set point. If the reading is less than the set point and building occupants are comfortable, the set point can be adjusted to the lower static pressure. And static pressure measurements must be taken at the same location in the distribution system as the pressure sensor that regulates the system operation, usually about 2/3 of the way down the main supply duct. If such a measurement is not possible or practical, the desired set point can be found by gradually reducing the fan speed each day until the pressure is as low as possible, but occupant space is still comfortable. And this change will significantly reduce the fan power requirements, reducing the static pressure. It's important to survey the occupants of the different spaces periodically to assess the comfort level. Are they comfortable with their air conditioning in their zone, or are they complaining? And so this will be a consideration. Now, in diagnosing the oversized fans in constant volume systems, it's not economically feasible to retrofit, if it is not economically feasible to retrofit to a VAV system, to convert the constant volume system to a VAV system. Resizing the constant volume system is generally a profitable choice. And the building maintenance staff is typically going to be limited to just one method of determining the potential for right sizing of the fan, and that is measuring fan system static pressure. If the supply fan is oversized, considerable energy can be saved by right sizing the fan in one of three ways. The first is larger pulleys. The fan has a pulley arrangement on between the motor and the fan in the fan room. And with larger pulleys, replacing the existing belt-driven pulley with a larger one will reduce the speed. And since the fan power is proportional to the cube of the speed, even small speed reductions can reduce energy costs appreciably. The new larger pulley should operate the fan at a reduced speed that still matches the peak load requirements. The static pressure adjustment to VAV systems consists of reducing the static pressure on a VAV system for reduction in the horsepower consumption. And by gradually reducing the static pressure in the VAV system, static pressure set point, to a level low enough to keep occupants comfortable, and fan speed will be reduced and thereby reducing energy consumption. In another opportunity on the fan is to replace the motor with smaller motors, smaller premium efficiency motors that are now on the market. Once the fan flow rate has been properly adjusted, the existing motor will probably be larger than necessary. Replace the existing oversized motor with a smaller premium efficiency motor that matches the load. For example, right sizing a 75 horsepower standard efficiency motor to a 50 horsepower premium efficiency motor could reduce, excuse me, could reduce motor energy consumption by about 33%. So a substantial saving is available there. Some of the premium efficiency motors operate at slightly higher speeds than the motors they replace. Because a fan's power consumption increases in proportion to the cube of its speed, it's important to compare the nameplate speed of the existing motor with its premium efficiency replacement motor. Now, diagnosing the oversized fans in the VAV system. We talked about that. And diagnosing the oversized fans in the constant volume system. And the variable, the thing that, as I've already indicated, the thing that has really made variable air volume systems, an excellent system from an energy utilization standpoint, is that the industry has developed variable speed drive motors. And so, and with the digital control systems that have been developed and are on the market now, the the variable air volume system, which in its original configuration resulted in the zones fighting each other to get the air. I want more air in my zone, but I'm going to have to take that away from some other zone. And then that other zone gets all upset and fights back and so on and so forth. But again, with digital control systems that are now on the market, the control system adds up all of the quantities of air that are being called for, and then it reduces or increases the speed of the motor, which increases the speed or reduces the speed of the fan as required. And this results in a substantial improvement in the comfort performance of the VAV systems and in the efficiency of the utilization of energy. So the the variable varying the fans converting to a variable speed drive for the motor on the fan is a good opportunity to look at to conserve the energy. So the as I previously indicated, the fan power draw is proportional to the cube of its speed. So reducing the speed can save a lot of energy. As an example, reducing the fan's speed by 20% can reduce its energy requirements by nearly 50%. And so installing a variable speed drive on the fan motor allows the fan to automatically match this reduced capacity, slowing down the fan in response to reduced demand, again, saving energy. This is a, oh, by the way, these PowerPoints that we're looking at today, there's more information than we're able to get to in a 2-hour discussion like this. But the you might want to get a copy of these PowerPoints from the PDH source. And I'm pretty sure that if you go to their website, log into your account and follow the instructions, that you can download a copy of these PowerPoints, and they may be of interest to you moving forward. And as an example, here is a case study, a real case study, a 12-story municipal building in Phoenix. The building originally had a constant volume dual duct system. So this is where you've got a cold duct and a hot duct. And when you get to the discharge point, there's a mixing box that mixes the warm air and the cool air to get it to the temperature that is desired by the occupants in that space. And in this particular building, there were 460 horsepower supply air fans and two 50 horsepower return air fans. In this example, the fan energy consumption was over 2.2 million kilowatt hours per year. And analysis of the building's load showed that the fans were considerably oversized, moving a constant 220,000 cubic feet per minute of air, when the peak load actually only called for 130,000 CFM. On the basis of this analysis, 2 of the supply fans and both return fans were disconnected, which resulted in an immediate saving of over 50% in energy consumption. And a bypass duct with this project was installed around each of the disabled fans in order to eliminate friction loss having to do with pushing the air through these disconnected fans. The remaining 2 fans in this example were converted to VAV by installing variable speed drives controlled by static pressure sensors in the ducts. The interior zone dual duct boxes were converted to VAV boxes by sealing off the connection from the hot deck and connecting a new pneumatic actuator to the cold deck damper that was operated by a zone thermostat. And the new system registered average savings of 70% compared to the constant volume operation, with a maximum demand reduction of 78%. And complaints from occupants decreased, and based on a conservative estimate of 50% average annual VAV savings, this $90,000 project saved 1.7 kilowatt hours of energy, worth over $135,000 a year, resulting in a payback period of only 8 months. So a big, highly cost-effective example. Now, modifying the controls on the system is an opportunity, and the 5 areas where this may apply are optimization of the scheduling of the operation of the HVAC system, when it's on, when it's off. Supply air temperature reset, in other words, is the air that is being supplied to the occupied spaces colder than is necessary. If you can reduce the temperature of the air that's supplied to the spaces, that's an energy saving there. Pressure reset is the static pressure coming out of the fan higher than is necessary to move the air from the fan to the occupied spaces. If it's too high, then you're probably doing something like using dampers to reduce the static pressure downstream, and that higher pressure takes more energy, of course, than if you have the pressure set where it is needed. Another important opportunity is economizer cooling. Now, an economizer is a system consisting of specially configured ducts at the fan room and appropriate controls. And the reason this is an opportunity is because there are times of the year when the outdoor air temperature is just exactly the temperature at which you would like to be delivering air to your occupied spaces. And when that occurs, you can turn off, if you will, the the flow of the cooling water into the cooling coil in the air handler. And on the other side of the coin, turn off the heating, the hot water flowing to the hot water coil in the air handler, and just use all outside air to supply your spaces. And so therefore you've eliminated a lot of energy consumption. And the economizer controls that are on the market, the digital controls and the automatic dampers and things like that that constitute an economizer system are now pretty much standard operating procedure on new buildings. But with older buildings, there is a likelihood that they do not have economizer cooling. The next control modification might be demand controlled ventilation. The quantity of outside air that is brought into the building for air quality control purposes has been specified in the ASHRAE guides and so on and so forth to be typically, so many CFM per occupant in the space, or so many CFM outside air per square foot of the occupied space. Just some rule of thumb type guidelines like that have been used in the design of these older HVAC systems. But there are now sensors on the market that sense the quality of the air that is being delivered and adjust the quantity of outside air to maintain the quality of the air that is needed in the occupied space. And this can be a substantial improvement in energy consumption, because the more outside air you bring into the system for ventilation purposes, why all of that air has to be either heated up or cooled down, whichever is required to meet the comfort needs in the occupied spaces. And that takes energy. So if you can control that quantity of outside air that is brought into the building for ventilation purposes using these air quality demand control systems that are now on the market, you're going to save energy there. So that's an opportunity. Optimizing the scheduling also. This is an operational matter, because you take a typical run-of-the-mill office building, and the occupants show up for work at, say, 8 o'clock, and they go home at 5 o'clock. So you turn the air conditioning off when the building is not occupied, or you keep it operating, but not cooling the air as much as when the building is occupied. So controlling the operation of the HVAC system to be consistent with how the building operates, how it's when it's fully occupied, when it's partially occupied. Maybe it is a building that has employees that show up at 8 o'clock in the morning, but the public isn't admitted until 10 o'clock. So optimizing the scheduling is a common sense control philosophy that can result in significant energy savings. To turn the HVAC system on and off when it is optimal to do so. Supply air temperature reset, and a typical office building would have the cooling coils designed to deliver air at somewhere between 53 and 55 degrees Fahrenheit to satisfy the cooling requirements on the hottest days. But during periods of milder weather, this temperature can be automatically reset upward to improve system efficiency by reducing the wasteful reheating of already cooled air. So outdoor air temperature sensor, when the air is when it's cooler outside, this cooling coil discharge temperature can be adjusted upward to provide energy efficiency improvements. So supply air temperature reset can be accomplished in different ways. Pressure reset is a method that can yield additional energy savings in systems that have variable speed drives installed. And pressure and flow are related. And so reducing the pressure supplied by fans also reduces the flow supplied, which in turn reduces the power requirement. So pressure reset is an opportunity that may exist with the control system for the HVAC. Here is another case study, where there was substantial energy and comfort improvements, and you can, when you get a copy of these PowerPoints, you can read through that, and it's interesting. Now, Economizer Cooling, a very good opportunity to conserve energy here. And this, you may be able to do this with just a reasonable amount of reconfiguring the duct work in the fan room, so that you have a way to discharge a certain percentage of the return air to the exterior of the building, bring in through another duct fresh air that is at just the right temperature for discharge into the occupied spaces, and you have a digital control system to determine, and you have dampers that open and shut, and so when the temperature outside is just right for what you want to discharge into the spaces, you can discharge all of the return air basically to the exterior and bring in all outside air. And with your fan then pushes that all outside air through the distribution system into the spaces. So economizer cooling is something to look seriously at. Sometimes a power exhaust fan is used with in conjunction with an economizer. In other words, the exhaust air the return air that you want to exhaust to the outside of the building, it may be appropriate and feasible to install a powered fan to suck that air out of the building. And in this example, with a powered exhaust, the cooling compressors only operated when the temperature was above 55 Fahrenheit. And the installation of the power exhaust system cost $75,000. And it paid for itself. It had a payback period of 4 years, under 4 years. So that was a good investment. Demand controlled ventilation. We've talked about this, that back in the old days, if you will, why the quantities of outside air that were brought into the building for air quality purposes, for ventilation purposes, was determined more or less by rules of thumb. So many CFM per person in the occupied space, so many CFM per square foot of space, and so on and so forth. But ASHRAE has written in too distant past, a standard that requires that commercial buildings bring in the specified minimum amount of fresh air to ensure the air quality. And this can be determined with air quality control systems that are now on the market. The premium efficiency motors, this is a good opportunity to look at, because these are a relatively new piece of equipment that's on the market, and they are it may be significantly cost effective for you to replace the fan motor in the air handler, and with premium efficiency motors be able to have a smaller motor that will still turn the fan so as to deliver the required quantity of air to the occupied spaces. So take a look at this, and you can change a fan, pardon me, a motor fairly cost effectively. With these premium efficiency motors, they do operate at higher speeds, and the motors have a synchronous speed, which is the speed at which the magnetic field within the motor is rotating, and a full load speed, which is the speed at which the motor shaft rotates when the motor is providing full load power. A motor's full load speed will always be less than its synchronous speed by a few percent. The difference between synchronous and full load speed is called slip. and the exact amount of slip a motor has depends on its design, construction, and loading. And this is where the premium efficiency motors come into play. Voltage balancing, three-phase induction motors are designed, specified, and rotated by their manufacturers on the assumption that exactly the same voltage will be fed to each phase and that equal current will therefore flow through the coils connected to each phase, generating a uniform magnetic field from each pole pair. But if you do not have a balanced three-phase power, then you will lose some of that efficiency. Also, another product that is on the market is energy efficient belt drives. In your air handler, of course, you've got the fan that's being driven by the motor, and there's a belt drive connecting the motor and the fan. And standard V belt drives are found in the majority of applications because they're the lowest cost option. But the newer V belts typically achieve efficiencies in the 90 to 95% range. A worn belt, however, can be considerably reduce the efficiency by slippage, and clogged V belts are similar, cogged V belts are similar to standard V belts, except that the normal flat underside has longitudinal grooves in it, allowing better grip and less slip than the standard V belts. So it may be cost effective to just replace your belts with the cogged V belts, which are more energy efficient. And the final item to be alert to is the need to employ, after you've made all of these energy improvement adjustments that we've been talking about, probably it's going to be a very good idea to have a testing and balancing contractor come in and rebalance the system. And that's a good idea. So the strategies to remember: address the zone level opportunities first, that is not in the fan room. Consider converting a constant volume system to VAV. It's a significant undertaking, but you can achieve a lot of energy efficiency improvement if you do that. Right sizing the fan system to match actual loads. And again, have there been other energy improvement features incorporated into the building, like more efficient lighting, solar glazing? And if so, that's probably reduced the total load on the air conditioning system, and you may be able to reduce the fan size and thereby reduce the energy consumed. Install the variable speed drives wherever practical, particularly if you're going to convert from a constant volume to a VAV system. Variable speed drives are a very important option to consider. Consider improvements to these controls, and then right sizing the motors, and use premium efficiency motors where possible, and install energy efficient belts. And that brings us to the end of our time. And since I don't like to ask people to stay after class, I'm going to bring things to a conclusion here. And I hope this was about what you were looking for when you signed up for it. And it gives you some, perhaps some ideas. Let's see. Let's see, somebody asks, who can see your messages? I'm not sure what that's referring to. Anyway, I'll bring things to a conclusion. I chat with you today, and now I'll just wish you all to have a nice rest of the day. So thanks a lot. Bye.